Section 29.5, the quantum mechanical hydrogen atom. We've just learned about Bohr's model, which worked quite well, despite the fact that it was based on some postulates which tried to handle some of the concerns that classical physicists saw but couldn't explain. And so he made some assumptions about the atom, followed it through to its logical conclusion using some of the Newtonian mechanics of orbits, for example, the centripetal acceleration. And he tied that with the Coulomb force, which is what keeps the electron in its circular motion. And he was able to derive some fundamental quantities about the hydrogen atom, including the size of its ground state orbit and the energy of its ground state and the energies of all the excited states. In 1925, Erwin Schrödinger introduced his theory of quantum mechanics, which was based on a complicated differential equation that we're not going to study, but it was analogous to the classical equation for energy, equal to the kinetic plus the potential. But it was applicable to quantum mechanical systems, and it was a more complicated differential equation that was actually complex in nature. So the Bohr atom is characterized by a single quantum number n, because Bohr was able to solve for the hydrogen atom, and it turns out in the hydrogen atom, n is what determines the energy. The angular momentum of the electron can take on different values based on the condition that the circumference contains an integral number of wavelengths. But the energy of the levels did not depend on its angular momentum, only n. In contrast to that, Schrödinger's analysis of the hydrogen atom found out that we needed to have more quantum numbers besides the principal quantum number n, and for heavier atoms, actually, it's necessary to compute the energy of the levels. They depend not only on n, but what we're going to call the orbital quantum number. So Schrödinger found the same result for the ground state energy and the excited state energies of the hydrogen atom, listed right here. And we're calling n the principal quantum number. Now, as we add in the angular momentum of the electron's orbit, it has value capital L, and it has units of h bar. And there's a small l, which we will call our orbital quantum number, L, and it can take on values anywhere from 0 up to n minus 1. So for a given n, let's just say the n equals 3 orbital, then the angular momentum of the electron can take on values with orbital quantum numbers 0, 1, and 2. And for those various values of angular momentum, you can compute the total angular momentum of the electron using this formula. But the only ones that the actual angular momentum that is relevant to experimental measurement turns out to be related to this little quantum number n. Okay, so the little quantum number n can go anywhere from 0 to n minus 1, and furthermore, it represents a vector, because it's an angular momentum, that can take on only certain angles with respect to the z-axis. It's discrete or quantized in the ability to line up with the z-axis. And so the shadow length, or the projection of that angular momentum onto the z-axis, can be thought of as m. And those shadow lengths can be anywhere from negative L all the way up to L in integral units, in integral values. So for a little l equals 3 state, for example, or let's say l equals 2, because that's one of the possibilities when we had n equals 3, little l could be 0, 1, or 2. If little l is 2, then we have the shadows on the z-axis equal to negative 2, negative 1, 0, 1, and 2. There's 5 total orientations of an electron's angular momentum on the z-axis for angular momentum equal to 2. Quantum number little l equal to 2. And then there's one more quantum number which we need to consider, and that's the electron itself has intrinsic spin, which is a quantum mechanical phenomenon that has no classical analog. We really can't picture the electron as a little sphere that's spinning on its axis because there are problems with that energetically, but it works as a picture in our mind's eye to imagine the electron as having a little spin quantum number. It's just not physically spinning. And it only has values negative 1/2 and 1/2 relative to the z-axis. So the spin quantum number, ms, can be negative 1/2 or 1/2, which corresponds to an angular momentum of 1/2 h bar projected onto the z-axis either positively or negatively, with projection negative 1/2 or positive 1/2. So here's the list of possible quantum numbers and the rules that guide them. For n equals 2, for example, in this table, we see that L can be anywhere from 0 to n minus 1. So we see that for n equals 2, the L values can only be 0 or 1. And for each of those L values, we have the possibility of m sub L, which is the projection onto the z-axis. So for L equals 1, we have the projections onto the z-axis of 1, 0, and -1. And furthermore, we also have the projection of the electron's spin along the z-axis. So for this collection on this side, we have little l equals 1, m equal -1, 0, or 1, and we have the spin of the electron in the positive configuration, or the positive projection along the z-axis. Likewise, we have that same combination of L and M with the spin quantum number projected onto the z-axis with -1/2. Now, these are all individual states with individual and unique combinations of quantum numbers. So all 8 of these states have the same energy in hydrogen. And you can see up here a summary of the rules dictating what values of little l based on the value of n can be, and what values little m can have based on the value of little l. These are rules that we're not going into in great detail, the reasons behind them, because that's more related to an advanced understanding of quantum mechanics. So what we've learned then is that the energy in the atom and the angular momentum are both quantized. The energy levels in hydrogen depend only on n, but for heavier atoms which have more than one electron, it turns out that the interaction of the electrons with each other causes the energy to depend not only on n, but on the angular momentum L of a particular electron. So the ground state would be the state with n, the principal quantum number, equal to 1, L equals 0, and ms can be either +1/2 or -1/2. We call this the 1s state. S historically stands for sharp, and the spectral lines that were observed for transitions to the ground state were seen to be fairly sharp, and that's where that terminology came from. For the L equals 1 levels, for example, when n equals 2, little l can be 1, and if little l is 1, then we call this a p state, and p stands for principal. If n equals 3, l can be as high as 2, and in that particular case, when l is 2, the atom or the electron is said to be in a d state, and d stands for diffuse, again referring to the appearance of the spectral line when spectroscopy was done on atoms. So these are the principal labels that we use for the various angular momentum states for an electron. If L equals 0, it's always called an L state, or an S state. If L is 2, then we always call that a D state. And that has to do with the angular momentum the electron finds itself with. Okay, so here then is a layout of the energy levels for the hydrogen atom and heavier atoms. But for the hydrogen atom in particular, these are the levels and their energies. So you'll notice for the ground state is 1s. The second state, n equals 2, can have a state with little l equals 0, which is the 2s state. But also, since n is 2, l is allowed to be 1, and in that case, we call that the 2p state. So for the n equals 2 state, we have two options, an L equals 0 and an L equals 1 version, which correspond to the S state, the 2S state, and the 2P state. Likewise, and notice that they have the same energy. We said that for the hydrogen atom, it doesn't depend on L. The energy only depends on N, and so therefore these two states have the same energy. We'll find that to be different when we consider in the next section multi-electron atoms. If N equals 3, then little l can be 0, 1, or 2, corresponding to the 3s state, where L equals 0, the 3p state, where L equals 1, and the 3d state, where L equals 2. And so on the vertical axis here, you see the energy as a function of n, and on the horizontal axis, we're simply separating out the various states by their angular momentum. The higher n is, the more number of substates we have with different angular momenta. Okay, so next we'll move on to a discussion of multi-electron atoms.